Welcome to our talk, OptFlow, a flow-based abstraction for programmable topologies. My name is Klaus Förster, and this is joint work with Long Luo and Manya Gobadi. So when you think of a wide area network, usually the first thing that not comes to your mind is flexibility. Indeed, if you want to change the topology of such a network, usually this only happens in the long term, namely when you deploy new fiber. However, you can still physically program the topology to be different, and not just in the long term, but also in minutes and in the future, maybe even in seconds. To understand this better, let's imagine that the wide area network is a graph where the fibers are edges and the connection points of those fibers are nodes. In order to carry traffic in such a wide area network, we have wavelengths on these fibers that then are steered at the connection points. So now, how can we now physically change this wide area network? To this end, let us look at a small example. Here we have 4 nodes that are connected by fiber, where on each fiber we deploy one wavelength. And let's say that these wavelengths can carry 1 unit of capacity. This then results in the following capacitated graph. This is a good assignment of wavelengths because this is traffic oblivious. It is the best assignment you can have if you don't know what sort of traffic you will get. Now let's say a specific traffic matrix appears where you send traffic from the left to the right side of the graph. Now the best thing you can achieve is a throughput of 2 because the cut between the left and the right side of the network is 2. However, note that no traffic is being sent between U and V and no traffic is sent between X and W. Hence, if we can steer the wavelengths to adapt to our traffic, we can obtain the following result, where we put 2 wavelengths between U and X and V and W, and hence we doubled our throughput. By steering the wavelengths in such a way, we can reach demand-aware capacity at the physical layer, namely by moving these wavelengths. Moreover, this shows that such topology programmability, abbreviated by TP, and traffic engineering, abbreviated by TE, can beat simple TE as shown in this example. So how can we in general leverage such TP? As we've seen before, optimizing TP and TE separately leads to missed opportunities and is not as efficient as it could be. Another version would be to redesign TE to include TP by cross-layer optimization. However, this is a tedious task and operators are reluctant to change their well-understood and well-running TE algorithms. To this end, we propose a third approach. Do not change your TE, but rather provide an abstraction that incorporates such TP. And in the next few minutes, I would like to give you a high-level intuition how to do so. So one thing that we want is that we don't want to change our traffic engineering. So what we want to have is that we apply our unchanged traffic engineering to an augmented topology, possibly with an augmented traffic matrix, and then as an output obtain flow routing and how to reconfigure the network. And we will do this with our earlier example. So in this example, we had that every node supports 2 wavelengths and every edge supports 2 wavelengths as well. So let us zoom in into one node U. In general, U should only be able to send 2 real units of traffic. So in order to do so, we propose to implement fake flows that block capacity. These fake flows represent a dual wavelengths assignment, where these fake flows block the traffic flow, leaving only space for the real traffic according to the capabilities of the nodes and edges. And the idea here is that TEs can handle real flows, and so why not represent programmability as flows as well, which we can then give it to the TE to solve. So to give you some intuition, what we will do is we'll say that U should have some fake flow that has to be sent to its neighbors. And then we also have the real traffic from U to X. And now we give both of these flows to the traffic engineering and ask it to assign it in some optimal way. In order to maximize the throughput, what will happen is that the fake flow will be assigned from U to V, whereas the real flow, which can only be sent to X, will be assigned from U to X. So let us look at this in a bit bigger scale. We have this 4-node network where we want to send traffic from left to right. Now let us add these fake demands that need to be routed, namely two to each, from each node to each of its neighbors. If we now implement this in the traffic engineering algorithm, both the fake flows and the real flows, what will happen is the following output, that these fake flows are sent on fiber which is not relevant for the real traffic, leaving the fibers for the real traffic unoccupied for the real flow. Moreover, these fake flows will completely block the capacities on fibers that don't need to be used, leaving the capacity of 4 free for the real flows. And if you remember the example some slides ago, this is then exactly also the output of the optimal cross-layer optimization. So to this end, traffic engineering, unchanged traffic engineering, can perform both TE and TP on our abstraction. Now, what we showed you here is just a high-level intuition. If you would like to see more details, then please take a look at our paper. So some other takeaways that we can get here is that we can now also get consistent updates, even consistent cross-layer updates, because consistent update methods know how to handle flows, and programmability is here depicted by flows. Moreover, our abstraction can also support major TE objectives, for example, maximum throughput, and also common constraints, for example, k-shortest path routing. What we also did is to test our idea in a test bed, here shown on the left side, some ROADMs with a logical setup on the right side. And what we will now do is that we send traffic from A to C over 2 different paths, and then fail a connection between B and D, such that we need to shift those wavelengths up from A to C. And when such a drop happens, our controller notices this, shifts the wavelength, and traffic can continue running. This is opposed to not having programmability, where you can see that the traffic drops and cannot go back up. Moreover, we also wanted to evaluate the performance on the runtime and on the throughput in larger experiments. So here, if we compare the cross-layer optimization with the standard ILP and with our approach called OptFlow on some wide area network topologies. And what you see here with respect to the throughput is that in an ILP setting, that the cross-layer optimization or abstraction has exactly the same throughput, where if we introduce some rounding for the LP case, we get slightly lower throughput. But again, the cross-layer and our abstraction formulation don't really differ much in the rounding case. Moreover, what we also see is that our abstraction greatly improves the runtime in this setting, because in a wide area network, the maximum degree is very small, so we only have very few fake flows that need to be optimized compared to a large number of wavelengths. So in order to summarize our talk, what we showed is that our abstraction enables traffic engineering to leverage topology programming in a wide area setting, where the main idea is to represent reconfigurability as flows, where we evaluated key items in a small testbed, and our simulation showed that our abstraction achieves good throughput and even better runtime performance. In future work, we would also like to look at further traffic engineering aspects and also to include amplifiers, long-range wavelengths, and some other more technical details. Thank you very much.